let's do practice problem number 8 on page 284. I'll read the problem out loud. It says a 400 gram sample of methanol at 16 degrees Celsius is mixed with 400 grams of water at 85 degrees Celsius. Assume there is no heat loss to the surrounding. What is the final temperature of the mixture? So given, we have some methanol. So here we have a little beaker of methanol. Now, these are probably not beakers. These are probably styrofoam cups or something that will prevent heat from the outside getting in or from inside our system getting out. It's kind of an artificial thing, but for a short period of time, you can say, hey, this will be true. And so the mass of this is 400 grams. The initial temperature of this was given to be 16 degrees Celsius. And and let's see. And it's methanol. And methanol, oops, you need to know the specific heat capacity of methanol. And if I look on the table on page 279, it's 2,450 joules per I think is it kilograms or grams? Let's see. Kilograms, kelvins. Kelvins. And then we're going to pour that into, mix that with some water. And of course the mass of this water is also 400 grams. The initial temperature is 85 degrees Celsius. And the specific heat of water is 4,180 joules of energy required to warm a kilogram of water by 1 Kelvin. Now, it's okay to mix degrees Celsius, by the way, with kelvins in this because we're really talking about temperature differences, and a temperature difference in Celsius is the same as a temperature difference in Kelvin. So we're going to pour this into here, and it's going to get all mixed up, and we want to know, find the final temperature. So let's solve it. Well, I like the drawing that Max made of this. I won't be able to draw it as well as he did. But once this is poured in here, think of it this way. You'll have some of the liquid at a higher temperature than the other liquid. Here's the water at 85 degrees Celsius, and here's the methanol at 16 degrees Celsius. And of course, heat will flow from high to low temperature. So heat's going to flow out of the water and into the methanol. Now, just like the video was talking about, if you have these two liquids separated, and one's at a higher temperature than the other, you have a highly ordered system. These molecules are all separated, and they're all at a different temperature, different amount of energy contained in them. And so, but when you mix them together, they're going to settle into a more disordered condition. They're going to mix all up. Now, we have the water. There's going to be heat lost from the water. and that heat is going to be gained by the methanol. But we say that this system is isolated from the rest of the universe. No heat energy is getting in, no heat energy is flowing out. So when I add the changes in heat of the water and the methanol, I'm going to get 0. Now, many of you started off with an equation that was solved for the final temperature. I'm going to derive that first. A few of you actually derived it. I was really impressed by that. So here we have the mass of the water times the specific heat of the water times the temperature change for the water plus the mass of the methanol times the specific heat of the methanol times the change in temperature for the methanol. So this is the heat lost by the water. It just gets poured into the methanol, that energy, that thermal energy. And so there's no net change in heat. So, well, let's go ahead and do this. This is T final minus T initial for the water. This is T final minus T initial for the methanol. But this final temperature is the same. So I'm just going to call it T final. But this T initial is the initial temperature of the water. This is the initial temperature of the methanol. So I'm going to have to distribute MC in here. Well, first of all, I can do a trick here. I could, if I wanted to, right now, cancel out the mass. And why is that? I can cancel out the mass because the mass of the water and the mass of the methanol are the same. But for right now, let's keep this general. The mass of the water times the specific heat of the water times the final temperature of the water. You have to use a lot of subscripts to do this. Minus the mass of the water times the specific heat of the water times the initial temperature of the water, plus, this is going to be a long line here, the mass of the methanol, specific heat of the methanol, times the final temperature. And you know what? I don't need the subscript there, do I? Because they're at the same final temperature. Minus T initial for the methanol. And that's all going to be equal to 0. So I want to solve for T final. So I'm going to distribute that out. This is going to be the mass of the water times the specific heat of the water plus the mass of the methanol times the specific heat of the methanol times T final equals, and then I'm going to put this on the other side. The mass of the water, specific heat of the water times the initial temperature of the water plus the mass of the methanol, put this over here, specific heat of the methanol times the initial temperature of the methanol. Then I'm going to divide by this. So rather than write out the whole thing again, I'll just do this. And this is the equation for the final temperature when you mix two liquids together, or you connect two solids together where you have a transfer of heat from hot to cold, and this will give you the final temperature. Now you can go ahead and start here. I don't expect you for all these problems to derive it each time, but I do expect you to know where it comes from and how to get it. Now now it's just a matter of plugging in the numbers. And to make we can go ahead and cancel out the mass because the mass of the water and the mass of the methanol they're both 400 grams. That makes it kind of nice. Makes it a little bit easier. So this is going to be for the water And you know what? I'm going to change from kelvins to Celsius. You can do that. Initial temperature, 85 degrees Celsius. And then this is going to be for the methanol. And then this is just going to be oh, I didn't even need to make that change because it's going to cancel out anyway. Notice that this whole thing, that whole group of units cancels out, leaving that. And when you plug that into your calculator, you get a temperature of, what was it, 59.5, I believe. Okay. Now, many of you just started here and plugged in your values and got this. I'll accept that, but I do want you to know where this comes from. Okay? All right. That is all.